there are two primary positive or polar structures that you can put on this nonpolar structure. One of them is this, and this is the most polar structure, OH. Okay, waters has an OH, alcohols have OHs on them. Ethylene glycol has OHs on them. A little, also highly polar, but a little less so, is an NH2 group on some carbon chain. Okay, what is this thing called? Yep, an amine. Okay, so if I have CH3 and an NH2, this is a polar structure, this is a nonpolar structure. So but now this is not quite as polar as this one is. All right, because the polarity difference, the electronegativity difference between oxygen and hydrogen is greater than that between nitrogen and hydrogen. And there's some other factors too, but that's all you have to consider in this class. Okay? Look at where oxygen is. It's a little further over than nitrogen. Nitrogen is a little closer toward the hydrogen. The electronegativity difference is a little less. Okay? So while this is polar, this tends to be a liquid, this tends to be a gas at room temperature and pressure. Tends to. Not is. That doesn't mean it is. It tends to. Does that make sense? We're getting into a situation where you have to start understanding that phase changes is somewhat relative. Even water. If you leave liquid water on the counter for a couple of weeks, what happens to it?
It gets nasty and it's warm.
Assuming it doesn't evaporate before that. Okay, so it'll evaporate. In fact, ice in the freezer evaporates.
So I thought it stayed cold.
Well, if you want to test me on that, take an ice cube, put it in the freezer, and come back 2 weeks later.
Ice cube is already in the freezer.
I know, but I want you to put one in there and not touch it.
Okay,
2 weeks.
In like a little cup.
That's fine. Just don't cover it up. It has to be open to the air in the freezer.
Okay.
Okay?
I'm going to do it. Right when I get home, I'm going to do it.
Okay. Eventually, that ice cube will start to shrink and go away entirely. And in 2 weeks, you should be able to see it much smaller. Okay? All right. So this has an effect just as much, just in the same way this does, just not as much of an effect. Does that make sense? So this creates a polar end. All right? But both of these have a special kind of polarity. The OH grouping and the NH2 grouping have a special kind of an effect on polarity. Okay? And it's called hydrogen bonding. Hydrogen bonding. Alright, hydrogen bonding is an especially strong kind of polarity. Hydrogen bonding is an especially strong kind of polarity. In fact, this word bonding here is there for a reason. All right. We said polarity is an attraction between molecules, right? Or it causes an attraction between molecules. So one water molecule, which has two hydrogens on it, and has a partially negative end on this side and a partially positive end on this side, should be attracted, should be attracted to another water molecule where the partially negative end is pointed that way. Right? Okay. Something kind of strange happens with hydrogen bonding. With hydrogen bonding, let's do this. Let's show this bent structure, okay? And let's not forget about those long pairs of electrons sitting up here. Or actually, one should come out and one should go back behind, okay? Here. Let's, we'll even draw that a little bit different. Yeah. Okay. Those are our electron pairs that are sitting up there. Hydrogens here and here. Okay. All right. So this water molecule, this hydrogen thing, end over here, the oxygen is pulling on the electrons, so they tend to spend way more time over here than they do over there. So this is the partially negative end. The electrons over here make it even more partially negative. And this hydrogen then, because it's has very little of those electrons around, okay? It's like a brother, two brothers or two sisters or something sleeping in the same bed and one's pulling the covers, right? The electrons are over here.
Doesn't that make you so mad?
Yeah, I know. Okay? So then this hydrogen is going to be attracted to one of those sets of electrons. Alright? Very strongly, because since the cover's it's looking for more cover over here, you might say. Alright? What's happening here is a little more complex than simply a strong polar attraction. What's actually happening here is a partial covalent bond.
When is it nonpolar?
Hmm?
When is it nonpolar? Because it's like, if it's unevenly distributed.
These are unevenly distributed. These bonds are unevenly distributed.
Is it nonpolar?
Polar.
Oh.
Polar bonds and an uneven distribution make it a polar molecule. Okay? So this is actually a little more than just a polar attraction. It's actually a partial covalent bond, not a complete covalent bond. It has a little bit of the character of a covalent bond and a little bit of the character of a polar attraction. Okay? In this class, we can think of it strictly as a very strong polar attraction, but in fact, it goes a little beyond that. And the latest research on the subject shows that to be the case. So the original term hydrogen bonding came from the fact that it was originally thought to be a type of covalent bond. And then new research seemed to indicate that it was more a polar attraction. It wasn't really covalent at all. But the latest research is it's a little bit of both. Okay? A little bit of both. Alright, so hydrogen bonding is really very, very important. Hydrogen bonding is what holds the two sides of your DNA molecule together. Hydrogen bonding is what holds the two sides of your DNA molecule together. It's what keeps your cells from being dissolved in the water in your bloodstream. Okay? It's this polar, non-polar thing going on that keeps you from basically falling on the floor in a puddle of goo. Okay? Yeah, it's pretty gross. I mean, you're basically just a bunch of chemicals, right? A bunch of molecules. And what keeps all that together, keeps it functioning the way it does, is because of the differences between polar and non-polar stuff in your body. The cell walls are non-polar. The water in your blood, and you're 70% water. Okay? You're mostly water. Okay? So what keeps you from being a puddle on the floor is that non-polar polar thing going on. Okay? So this is very important. What?
If it was like all polar, then it would be like a puddle.
Well, if you were all polar, then you'd have no flow of materials through your body. The water in your body allows all these things to take place. The ion exchange, that allows your muscles to work. The electron transfer, that allows your cells to work. I mean, your nerve cells to work. Allows you to see and talk and all that here. The let's see. The flow of the blood cells through your body that allows the oxygen exchange with the CO2. Okay, and that's all polar, non-polar stuff. Okay, all that's polar, non-polar. So this polar versus non-polar is really important to anybody who has an interest at all in a medical career or in any kind of engineering career or any kind of chemical career. Okay? I bet that covers most people in this class. Okay? Has an effect in music. Has an effect in cooking. There's a whole organization called America's Test Kitchen. They use scientific principles to find out better ways to cook food, to make better dishes. It's all about chemistry.
Does it help to be a lawyer?
What?
Does it help to be a lawyer?
A lawyer?
Yeah.
Yeah. Sure. How are you going to explain environmental issues to a jury if you don't understand it yourself?
Well, I mean,
And environmental issues are based around this polar, non-polar thing. Okay?
what if I want to be
Really? Do we want to parse down every single career that's out there? All right. So you are a football coach,
Yeah.
and you're trying to help your receivers catch the ball. Polar, non-polar.
Oh, it works for everything.
Okay. How are you going to teach your players to function more effectively in different weather conditions?
Polarity.
Polar, non-polar. Okay. If you the more you understand about a lot of different things, the better you are equipped to do just about anything.
That's true.
Okay. All right. Now, let's back up just a minute and let's talk a little terminology again. All right. So this kind of attraction between these large molecules, those are called London forces. It's named for a person, not the city. This attraction between these temporary polar locations are called London forces. London forces.
Like the country?
Like the city, but it's named for a person and not the city in England. Okay? These temporary dipole locations. Okay? Those are called London forces. They're also sometimes called van der Waals forces.
So it's like they're trying to figure out who first.
No. It's London and van der Waals, when you get into higher level chemistry, start to mean something different, but at this level they're kind of talking about the same stuff.
That's beyond the
Yeah, kind of beyond the scope of the class. So if you hear me use the term van der Waals or London forces, at least at this level, at this time, they kind of mean to us the same thing. Okay? All right, so London kind of described the whole idea to start with. Van der Waals actually did the math on it and does the mathematical calculations that go into some of that. Okay? All right, so I have not only do I have that Venn diagram, but I have a kind of an organizational diagram in the unit handout. Okay? Called looks at structural particle attractions. This is something you probably need to do your best to commit to memory. And not only commit to memory, but try to understand how this all works. Okay? So structural particle attractions. Okay? For molecular attractions have to do with those London forces and dipole-dipole forces, because some molecules are polar and some are nonpolar, and there's some kind of in between. Okay? The kind of particle attractions between ionic, are called, that is, between a molecule and an ionic substance, is a attraction between ionic, is called a dipole and ionic force. So when we dissolve salts in water, they dissolve because those charged particles are attracted to the polar ends of water. The positive ions are attracted to the negative side where oxygen is located. The negative ion is attracted to the positive end where the hydrogen is located. Okay? So that's a dipole ionic force. And then the structural particle attraction in ionic compounds are strictly the ionic attractions. The opposite charges being pulled together. Okay, very strong attractions there.